I start recording. So the goal of this lecture is to continue with the maximal extension of Schottky geometry and then talk about conformal compactification or Penrose diagram. Let me just remind you that so what we learned on Wednesday, so we learned about the Kruskal extension of Schottky geometry. So we started from the Schottky geometry in coordinates t and r and theta and phi, and then we changed the coordinates from t and r to this new null coordinates big U and big V, in terms of which the metric the line element looks like this. So the line element looks like ds squared equals minus rg over r e to the minus r over rg times dv du plus r squared d omega squared. And we also said that now we can also introduce time-like and space-like coordinates. Once we have the metric in this form, we can introduce now, we can call u to be t minus big T minus big X, and big V we can call it big T plus big X. So in terms of these T and X coordinates, the metric will look like Rg over R e to the minus R over Rg times minus dt squared plus dx squared. So this is just a 2D Minkowski metric. And then there will be the spherical part. And then I drew a diagram. Oh, and there was a constraint on U and V. And that implies also a constraint on T and X, which was that there was an actual singularity in this metric when R is equal to 0. That was a physical singularity, and that was located at UV equals 4G squared. So the condition is that U times V has to be less than 4 RG squared. So now what is the nice feature of this metric? The nice feature of this metric, this form of the metric, or this form of the metric. The nice feature is that these are, if we look at the two-dimensional part, basically the time and radial part of this matrix, they are of the form which is called conformally flat. What does it mean? It means that it's just a factor, an overall factor times the flat 2D metric or Minkowski metric. Why is this form useful? It is useful because the trajectory of the null rays when we have non-conformally flat metrics is extremely simple. The null rays in these Tx coordinates are going to be 45-degree lines, or in this UV coordinates, there will be constant U and constant V lines. And why it is useful to have a simple form of null rays is because the null rays determine the causal structure of the space-time. So the causal structure becomes very simple or very obvious once we write the metric in a conformally flat form. So therefore, I can draw a diagram like this, and we can analyze the causal structure of the diagram. So for instance, there was this. So we started from the region when R was larger than Rg, and that was this region. So that was the original patch that the Schwarzschild coordinates would cover. And then we learned that if we follow the infalling null geodesics, we can extend it beyond R equals RG. And also if we follow the outgoing null geodesics, we can again extend beyond R equals RG. And then we can even extend it, even beyond that to get this full geometry. So now this full geometry that we obtain here, it has 4 distinct regions based on the causal structure of this metric. These 4 distinct regions. Sorry, is there a question? When you say conformal, what do you mean? Well, so well, in this context, but I guess also more general, conformal means that it's the word means have the same form. Now, in this context, what it means is that the metric will be a factor times the flat metric. That's what I mean by conform. So here I call this metric or this part of the metric, I call it conformally flat. What I mean is that it is of the form some overall factor omega squared times ds squared of 2D Minkowski. Did I answer the question?
Yes, Professor. Thank you.
All right. So yes, we have this. Another thing that perhaps I didn't mention is that once I draw this diagram here, this diagram is, I have suppressed this sphere, right? It's a two. We are talking about the 4-dimensional geometry, but of course, in order to draw it, I can only have 2 of the dimensions. So I have every point in this diagram corresponds to a sphere. And R determines the area, R determines the area via 4 pi R square. Okay, so there are 2 distinct regions in this diagram. So this is region 1, this is region 2, region 3, and region 4. So region 1 is the one that we started with, is called the exterior region. But now there is another region 3, which is exterior region of this extended geometry. And as we can see in this diagram, these 2 region 1 and 3 are causally disconnected. There is no signal that I can send from region 1 that arrives to region 3 and vice versa. No signal from region 3 can arrive to region 1. So these two exterior regions are causally disconnected. How does the spatial slice of this region look like? These are the exterior regions, so they look like the geometry that we have outside of a star, for instance. So if I want to look at the spatial slice of the geometry, spatial slice in region 1, how would it look like? So it but pictorially it looks like this. Now, if we have a star, then at some point this there will be some matter distribution, and then you should think of this as describing the. So, if you like, this is really a one-dimensional reduction of the spatial size to one dimension. So a sphere is zero-dimensional sphere, which is 2 points. But if you can imagine, this could be, I can go to one more dimension. I can imagine this is, I guess this is not a very good drawing, but perhaps you understand the idea. So there will be some surface that the size of the so the symmetric spheres that we had in Schwarzschild geometry. Remember, we said that Schwarzschild geometry has a spherical symmetry. So those spheres are the contours of constant spheres are like this, and then they shrink as we go deeper in this potential way. But if we have some mass distribution like a star, then that radius of the spheres, they smoothly shrink to zero. Like if we have the Earth or the Sun, we measure the size of, we have symmetric spheres, and as we go closer and closer to this body of mass, we get to a smaller and a smaller radii, meaning that the area of these surfaces or these spheres will shrink and eventually shrinks to zero. That would be the center of the Sun or the center of the Earth, where the area shrinks to zero. So this is when we have a mass. So here there is say mass of the star, or matter in general. It's called matter. And here R shrinks to zero, or let's write it R. Now, if we consider, so this was not Schwarzschild. This is just this will be just a star. But now, if I want to consider, Schwarzschild geometry, then as I go in, there is no mass distribution. Schwarzschild geometry is a vacuum solution, so there is no matter in it. As I go in, the radius of a sphere shrinks, but then it bounces back. And so this is actually not just region Wu, this is region 1. This is just a spatial slice. Going through region 1 and 3. So if I consider in this geometry, if I consider a slice, the spatial slice that moves through this point in the middle, then that spatial the slice has this particular form, except that every 2 points on this you should really think of it as a 2 sphere. So it's hard to draw it, but that's how it is. That's what it is. And this middle point, if I choose a slice that goes through that point, that central point of my diagram, which is called the bifurcation horizon sometimes, at that point, the radius, the radius or the R that determines the area of a sphere at that point will be RG. So it shrinks to the smallest value, RG, and then becomes larger again. Now here we have two asymptotic regions. So as we go far away, so this is these regions are becoming approximately flat because we are going far away from the gravitational source. Like if you imagine you are an observer here, very far from this gravitational source, it wouldn't from the gravity point of view, or the geometry doesn't look different from that of a star with the gravitational radius RG. As we go far enough, that gravitational force decays like a gravitational field decays like 1/r, and we eventually become closer and closer to Minkowski. So far away is we call it asymptotic Minkowski. And now we see that there are two asymptotic Minkowski regions in this extended geometry. So one is on one side, and so this will be region 1, and then this will be the observer in region 3. And again, there is asymptotic. Region 3 is also asymptotically Minkowski. Okay, so this is the spatial slice of the geometry. There are two exterior regions, and then these exterior regions, both of them are asymptotically Minkowski, which corresponds to these regions far away on these two sides. Okay, now there is this region 2, which is called the black hole region. Why is it called the black hole region? It's because as you can see again, this is a diagram which clearly shows the causal structure. This is a diagram in which the light rays travel at 45 degrees. So we see that from this region, nothing can escape outside. That's why it's called black hole region. Things can go in, but they cannot go out. And then eventually every causal curve, every time like or null curve will hit the singularity at r equal to 0. So that's why it's called the black hole region. And then we have this region 4, which is called the white hole region. So this is just the opposite of the black hole region. Things can go out of white hole region, but no signal can go in the white hole region. These regions have r less than rg, and then there is a boundary, or there are boundaries of this black hole and white hole region, and those boundaries are called horizons. So those horizons are at the points r equal rg, which corresponds to uv equal to 0. So either u is 0 or v is 0. U equals 0 or v equal to 0, these are this translates into r equals rg. And also these are null hypersurfaces, because remember that the constant u and constant v lines are null lines, right? Because if you see from the metric here, if I set u or v to constant, then and I consider radially moving ray, radial means that there is no motion in the theta and phi direction. So this part is 0. And then if I say u is constant, then du will be 0. So therefore the line element vanishes. Or if I say v equals constant, again, the line element vanishes. So I'm talking about null rays here, radially moving null rays. These are radially moving null rays, but the value of r actually doesn't increase along this null rays. So these are null rays which are radially moving, but they are stuck at r equals rg. So I guess one way to think about it is that the gravitational attraction is so strong at that point that the null rays cannot escape to infinity. So anyway, this null hypersurface is called black hole horizon, and this null hypersurface is called white hole horizon. What else? Let's see. What else I wanted to say about this? Yeah, okay. So the last thing that I wanted to mention about this is that this diagram is, or this extended this extended geometry is somewhat abstract, meaning that we don't have such a thing in our universe, because this is just a vacuum solution. It's a particular vacuum solution. What we have in our universe are black holes which are formed from the collapse of matter, and when we have matter, then the geometry will be different inside the matter distribution. So this was just a vacuum solution. Sorry, just a moment. I should close. Okay. Yes. So if I have matter distribution, then the geometry will change. So normally, what happens is that when we have black holes that are formed from the collapse of matter, say from the collapse of a star, then I won't have all parts of this geometry. I will have some regions, some parts of region 1 and parts of region 2, but the region 3 and region 4 will not exist in those cases. Now we will get back to it later when we talk about Penrose diagram. Okay, so let me know if you have any question about this part. Otherwise, we move to conformal compactification and Penrose diagram. Okay. So we saw that it's useful to write the metric in a form which is conformally flat. It is useful because it makes the causal structure of the manifold obvious. Now we want to make one further step to bring everything to a finite region. So if you remember, in the case of charges, for instance, this big U and big V coordinates would run were uncompact, or would run over the full real line up to some constraints. So there were points at infinity in that diagram. Now, one thing useful to do is to compactify this diagram so that we bring even the points at infinity to finite points. So then I can draw a diagram that really includes all of the points of the manifold, even the asymptotic region or asymptotic infinity. So let us start from the example of Minkowski spacetime, which is easier, and then we apply the same logic to the Schwarzschild geometry. So we start from 4D Minkowski. Where the metric, if I write it in radial coordinates, is minus dt squared plus dr, or in the spherical coordinates, it is minus dt squared plus dr squared plus r squared d omega squared, right? And then as before, I'm going to introduce null coordinates. So here I define u to be t minus r and v to be t plus r. Now, in terms of this u and v coordinates, the metric will be minus du times dv plus r squared d omega, where again r should be thought of as an implicit function of u and v. Oh, and another thing is that, so here we know that t runs between minus infinity to plus infinity, and r runs from 0 to infinity. So the fact that r runs from 0 to infinity, it means that, again, this u and v are ranged between minus infinity to plus infinity, but they are subject to a constraint. The constraint is that r is larger than 0. But what is r? R is v minus u divided by 2. So v minus u divided by 2 should be larger than 0. Which means that v has to be larger than u, or larger than or equal to u. So this is equivalent. So this is equivalent to saying that r has to be larger than 0. Okay. So we have this. So in terms of these coordinates, we have the metric. Now, one thing that we can do now is to, or that was the goal of now this lecture, is to compactify, again, this two-dimensional part of the metric. So this is a technique that is applicable when we have enough symmetry that we can, or it's useful to restrict ourselves to a 2D part of the metric, and we find a two-dimensional diagram which is compact. So here I want to focus on the UV part of the diagram, and we want to make the range of U and V compact. And we do that by using some functions that map the entire real line to a finite region. For instance, we can use tangent hyperbole, and we want the functions to be monotone. So I define U bar to be tangent hyperbolic of U, and V bar to be tangent hyperbolic of V. Now, in terms of this U bar and V bar, then the metric is going to look like minus du bar dv bar divided by 1 minus u bar squared times 1 minus v bar squared. again plus r squared d omega squared, where r should be thought of as the function of u bar and v bar. Now, now what have we achieved here is, what we achieved is that we express the metric in terms of some coordinates that now range between, so what range between 1 and -1. Why? Because u and v, they range between -infinity and +infinity, and tangent hyperbolic maps the variables, the maps the real line to the interval -1 to 1. So therefore, what we have is that, again, I write it here, u bar and v bar are between -1 and 1, subject to the constraint that v is larger than u. So that is, that we had here, v is larger than u. But since tangent hyperbolic is a monotonic function, that also translates into v bar larger than u bar, larger than or equal to v bar. In particular, the point r equal to 0 corresponds to, or not the point, the locus of r equal to 0 corresponds to v bar equals u bar. Okay, so now this metric that I have here, or the two-dimensional part of the metric, is again conformally flat. It has this factor, or this prefactor times the flat metric. This du dv is the flat metric, but also the u and v have a finite range. So it has two good properties. One is that it makes the causal structure obvious, since it is conformally flat. Moreover, it is compact because u bar and v bar are compact. So if I want to draw a diagram for just this, for the 2D part of the metric, that diagram will look like this. So I have to draw 45-degree lines because these are null coordinates. So this will be my v bar, and then this will be u bar. Then there is the point on the locus, the set of points, or the lines when v bar is equal to u bar, and that's the origin, r equal to 0. And then what we said is that the range of u and v is between -1 to 1, subject to that constraint. So if this is 1, then we have the following diagram. We'll have a diamond. Okay, something like this. So this dotted line is the r equal to 0 line. So we really we want to have v bar larger than u bar. So what it means is that we are to the right side of this r equal to 0 line. So this will be the region that we have. Or if I want, we can even write it, draw it again separately, so it will be really just a triangle. And so this was 1, 1, minus 1, minus 1. Now, so what, so again, this is r equal to 0. Now, so what we have achieved is that now we have drawn the full Minkowski metric, at least the T and R part of the Minkowski metric. We have compactified the whole thing into this this little region. Now, why is it useful? It is useful because now it makes the asymptotic structure of the manifold simple. For instance, we can ask what would be the trajectory of a curve, a null curve that passes through the origin in this diagram. Or we can ask, where do null curves in general end up when they go to infinity? At infinity, in infinite future, where do null curves end up, or where do time-like trajectories or time-like observers end up in this diagram in the infinite future? These are questions that you couldn't ask before before this compactification, because infinite time would go outside of the limits of your page. So there are these important regions of this diagram. There is a scry plus, which is called the asymptotic null infinity, future null infinity. And then there is a scry minus, which is asymptotic past null infinity. So asymptotic future means infinite future. Null infinity because the null rays will end up there. Asymptotic past null infinity is because the null rays in the infinite past, they start from that point. Then there is I plus, which is called the asymptotic time-like infinity, and I minus, which is asymptotic past time-like infinity, because the time-like curves would end up there at infinite time. And then there's a spatial infinity, I0. Let me for a second look at this. Okay, so it's I0. So yeah, maybe it might be useful now to let us try to verify some of these things. Let's see. So for instance, so I call this oh, by the way, this is called the scry plus because it's a script I plus. So this is, sometimes it's called the scry plus. And this one is called the scry minus. So let us verify some of the statements that I mentioned. So for instance, we want to consider a null ray, that an outgoing null ray, right? So what is the trajectory for an outgoing null ray? This is just a radially moving null ray. What would be the trajectory of that in Minkowski spacetime?
It's just 45-degree parallel to scry minus.
But can you give me the equation? So in terms of T and R variable, I want the equation for a null ray. For instance, R as a function of T.
R equal to T.
Okay. So if I want to consider an array, radially moving outgoing null array. So we say R is equal to, so Arpon says that it's R equals to T. It could be R equals to T plus any constant, right? Because this one is at the origin at R equal to 0, at T equal to 0, but it could be at the origin at any time. So more generally, it will be R equals T minus some T naught. Right, we are in Minkowski space, so this, everything is just simple. Okay, so now if R equals T minus T naught, then we want to ask what happens to these coordinates U and V, right? So what was U? U was T minus R, so this is R of T, T minus R. For this particular trajectory, T minus R is equal to T naught, right? And if I look at V, which is T plus R, for this particular trajectory, is going to be twice T minus T naught, right? Now, imagine I take the limit that T goes to infinity, right? So infinite future. We want to see what happens at infinite future. At infinite future, when nothing happens to U, because U is a constant here, but V goes to infinity. So at infinite future, U is again equal to T naught, but V is equal to infinity. Now we can go to the U bar and V bar coordinates. So U bar was just tangent hyperbolic of U, which means tangent hyperbolic of T naught. And V bar is tangent hyperbolic of V, which is infinite. Tangent hyperbolic of infinite is 1. So V bar is equal to 1. Now let us go back to our diagram. So our diagram was here. So this is V bar. V bar is a null line, a null coordinate. So its axis is at 45 degrees, and U bar is also null. So we said that as T goes to infinity, this null array will end up at V bar equals to 1. And U bar equals tangent hyperbolic of T naught. In fact, U bar is constant along this trajectory. So if I want to draw this trajectory on this diagram, so it is something at the constant U bar, and then V bar as time goes to infinity will go to 1. So this will be the trajectory, right? If I assume that T naught is, say, positive, then it will be something like that. So eventually, as T goes to infinity, I'll end up on this line. So this is why this region is called the asymptotic, future asymptotic null infinity, because the null rays, the outgoing null rays at infinite time in the future will end up on this line. So as I change the value of T naught, then this null ray will end up at different points along this V bar equals 1 line. So that's where the null lines will end up in the infinite future. Similarly, if we ask about an ingoing null ray, so a null ray that as time passes, it goes to smaller R's, then if we go to the past, that will end up on this line. That's why it is called past null infinity, because at the infinite past, the null rays would end up in this region. Now, we could also ask the similar question about time-like curves. Just consider some trajectory of a time-like curve, for instance, a curve which is sitting at constant r, and ask where does it end up as I take t to infinity. So in fact, I want to ask you to do it now. And maybe write. Actually, there are, maybe I can add these 2 questions that you can try to think about now. So exercise is, one of them is to, so A, mark the point r equals infinity, t equals constant. B, draw the word line of an observer at r equals constant. Okay, so yeah, so after this exercise that we didn't record, and now we go to the case of the Penrose diagram for the extended Schwarzschild geometry. And the idea is exactly the same. So it's very simple. I just copy this metric, and then it should be completely obvious that what we should do. So we copy this. Yeah, so this is the metric for the extended Schwarzschild geometry, and now all that I need to do is that I apply this monotonic function that maps the Fourier line to a finite interval, namely the tangent hyperbolic function, to this big U and big V, and then we are done. We get the compactified metric. So all that I need to do is to call U bar tangent hyperbolic of U and V bar to be tangent hyperbolic of V. Now what happens is that, so this, again, this U and V would range from minus infinity to plus infinity, subject to this constraint. In terms of this V bar and U bar variables, that would correspond to, so I draw again this these 45-degree lines for V bar. And U bar. I know that the range, let me make it a bit smaller. So I know that the range is between 1 and -1. So I will again draw this diamond. And then we had this point, this constraint that u times v is less than 4rgs squared. Now imagine u goes to infinity here. This is a constant in u times v. So if u goes to infinity, v has to go to 0, right? If I want to be at this point. Now, what does it correspond in terms of u bar and v bar? So we said, so let's actually write. So we say if u goes to infinity, then v has to go to 0. Of course, at the point, at r equal to 0. At r equal to 0, which is defined by, so r equal to 0 is equivalent to uv equals 4rg squared. At r equal to 0, what happens is that as u goes to infinity, v goes to 0. That corresponds to u bar equal to 1 and v bar equal to 0. And as v goes to infinity, u goes to 0, which corresponds to v bar equals to 1 and u bar equal to 0. Okay, so these are these two points are these 2 points here. Let me write in red. So there are these 2 points. Similarly, we can send u and v to -infinity, and then big V and big U to 0 from this. So these were actually, I should here said that U and V go to 0 from the positive direction. Similarly, we could send them to 0 from negative direction, and the other variable to -infinity. And those would give me, let me draw it with a different color. Those will give me these 2 points. And then the rest is, again, we can determine exactly what is the trajectory of this line, r equal to 0, because we know exactly what is the relation between u and v and u bar and v bar. So if you do it, you can actually plot it and find the analytic expression. But the important point is that this is a space-like line or hypersurface. This r equal to 0, r equal to 0 line. Why? Because r becomes a time-like variable when we go inside the horizon. So in this region, r is time-like, while in this region, in the exterior regions, r is a space-like. So here r is time-like, and therefore r equals constant. In particular, r equals 0 is a space-like hypersurface. Now the shape of the space-like or time-like hypersurfaces are not really important or very meaningful in Penrose diagrams, because I could choose different monotonic functions, and those monotonic functions of this u and v, and that would change the shape of the time-like or space-like curves. As the only thing that it preserves is the light cone. So the only thing that is really robust in this Penrose diagrams is the causal structure or the light cone. The shape of the time-like or null or the space-like curves can be modified. Therefore, it is very common to draw it just like a straight line. You could choose some monotonic function that makes it a straight line, even though with the choice that I made, it's not really a straight line. If you find the actual function, it will look like this. It's still a space-like, but it's not a straight line. Anyway, this is the let me draw everything now in black because now it might look confusing. So this is the Penrose diagram for the Schwarzschild geometry. This is region 1, region 3, the exterior regions. This is the black hole region. And this is the white hole region. And finally, if we want to consider a black hole formed from the collapse, then the past of that spacetime would not look like this, right? So what do we want to consider? We want to consider a star or some distribution of matter in the far past, and in the future it's gonna collapse into a star. So in the past it would look like Minkowski spacetime plus a bunch of matter fields inside it. So before that, is there any question about this? Okay.
Professor, sorry. After these coordinate transformations, we also have that region 1 and 3 are also causally disconnected, no?
Yeah.
I mean, we preserve everything. Okay, thank you.
Yes. But the causal structure doesn't change. And we see it here that they are causally disconnected. The good thing that happened is that the infinities now are at finite points. Right? Before we had infinities at infinity. Now they are at finite points. So now you can see where the null curves, when do they start their life and when they end, where they end, and where is the time-like infinity, where is the space-like infinity. Okay, so now we want to look at the black hole what is it? Collapsing star. Black hole formed from a collapse. Now, in the past, this should look like Minkowski plus some matter. So let us draw the past part of the Minkowski. So remember, this was the scribe plus, this was I minus, and now I have some distribution of matter fields. Say it's time-like, so some massive object. So they start from I minus, but then eventually it's going to collapse into a black hole. So the future part of the diagram will change. There will be, so outside this matter distribution, there should be Schwarzschild geometry. So outside, the Penrose diagram will look like the Penrose diagram of Schwarzschild that I just drew. But inside it is different. Like in particular, inside here, I have R equal to 0. So as I said, if I have matter distribution, R just smoothly goes to 0 inside matter distribution. Except that at some point it collapses. Once it collapses, then I form the singularity. Okay, so now this doesn't look Very good. So this is my matter distribution. This is again not good. Okay, this is better. So that would be the Penrose diagram for a star collapsing into a black hole. In the past, it looks like some matter propagating on Minkowski spacetime. But then when it collapses, then outside we have this a piece of region 1 and a piece of the region 2. Of the geometry. Okay, so I didn't talk about the names that we give to these asymptotic points in the Schwarzschild case, but they are analogous to the Minkowski set. So this is a spatial infinity which is called I0, and this is time-like infinity. So the time-like observers who avoid falling inside the black hole, falling inside the singularity will end up here. While the other ones who fall inside the black hole, singularity. So this will be R equal to 0, and this is also the R equal to 0 singularity of the Schwarzschild geometry. Okay, so that's it for today.
I have one question from the Penrose diagram of Minkowski spacetime.
Okay.
Can you go back?
Yes. Here.
I mean, in the Minkowski spacetime case, can we extend our region to the left side?
No, we cannot. Because at this R equal to 0 is, at that point, the geometry just ends. So we have this constraint that it's not R equal to 0 is not a, it's just a limit of these coordinates, like this coordinate that we had. So let me say it this way. This full diagram is the Penrose diagram for the 2D Minkowski spacetime, right? So just looking at it, looking at it as a two-dimensional metric, you could go beyond that point. But considering the fact that it came from a 4D metric, then R equal to 0, there is just the boundary of it's the limit of R. It wasn't the coordinate singularity that we want to go beyond that. So then no, for if it's going to represent a four-dimensional Minkowski or higher dimensional Minkowski, it's always like this. It's this triangle region with R equal to 0 corresponding to this one. R equal to 0 has a meaning here. Is the point when the area of the sphere shrinks to 0. And that means that you smoothly end the geometry at that point. While if we were just in 2 dimension, there was no sphere factor, then you would just, that would be actually a point that you could extend your geometry beyond that, because the geometry doesn't actually end at that point if you didn't have the sphere factor to shrink.
I mean, in the example of Schwarzschild metric, the kind of regions we worked with, like the region on the left side or the other regions. Initially, we didn't have access to those regions in our initial coordinates. Then we went to the coordinates of U and V, and then we extended the region of U and V.
Yes.
In the regions we initially started with. So can we do something similar to this in this case?
Well, there we saw that if we extend the coordinates beyond that point, then we'll get the smooth manifold. Like for instance, we could consider geodesics. So there, for instance, what were we doing there? Well, there we were limited to this region, actually, to this quadrant. These 2 points there would be, let's see if we have it. We were here, right? And these were R equals RG. So the size of the sphere was finite. And then we saw that we can have geodesics or just infalling observers who go through this point and outgoing observers who go through this point. And similarly here, so we smoothly extended the geometry beyond that. In this case, if you consider geodesic, so this is a good exercise. If you consider geodesic, a null geodesic in Minkowski, in 4-dimensional Minkowski, in this radial coordinates, it actually bounces back at r equal to 0. So r equal to 0 is a point when the sphere shrinks to 0. If you were to extend this geometry beyond that, it would be like having 2 copies of Minkowski spacetime. There would be no connection between these two. The null rays on one of them would just come here and bounce back, and the null rays on the other one would just come and bounce back there. That diagram would be the diagram of 2 Minkowski spacetimes where you have just identified or put next to it together 2 particular trajectories in this diagram. So now if you identify them, it actually won't be a manifold anymore, because now you have an intersection at that point.
Yeah, I see. Thank you.
I also have one question.
Yeah.
Is there any general constraint for the compactification of a metric, or we can compactify any metric?
Well, any 2-dimensional metric can be written in a conformally flat way. And once it is conformally flat, then you can compactify. However, but now we generally deal with 4-dimensional metrics or higher dimensional metrics, not 2-dimensional metrics. And whether or not we can restrict ourselves to a 2D subspace is a question which depends on the particular case. So when we have symmetries, it's useful to restrict. But like when we have a spherical symmetry, it's useful to restrict to a subspace, a 2-dimensional subspace, a TR subspace of that, and then compactify that. But if there is no symmetry, in principle, you could pick 2 coordinates and try to compactify those, but it wouldn't be that helpful. Oh, actually, another constraint is that it has to factorize, right? So this 2-dimensional part would factorize compared to this sphere part. So that otherwise, if generally it wouldn't, the metric wouldn't have this factorized form, in the sense that you couldn't write it as the metric of a sphere plus another TR part of the metric. The most general metric might not have this factorized form, that you can write it as a piece which depends on some coordinates and other piece that depends on the other coordinates. Yeah, so this is perhaps the more constraining factor. We had a piece of the metric that only depends on one or two variables, say this TR part of the metric or UV part of the metric. There might be generalization of this that I'm not aware of. The cases that I know are only when you can identify 2D part of the metric.